Hey guys, so this is a short recording for just some pretty easy or like rather more intermediate, no, more basic-ish colorimetry problems. These colorimetry problems aren't gonna be the bomb colorimetry problems. They're gonna be the coffee cup ones. So anyway, let's start. So let's read the problem. 2.50 grams of zinc was dropped into 65 grams of water. The water started off with 20.00 degrees Celsius, but later on, it rose to 22.50 degrees Celsius. What temperature did the piece of zinc start off with? And it also says here that your zinc will have a specific heat capacity of 0.390 joules per gram Celsius. So before we start, we gotta list down all our variables, right? So let's make a table. So here we have zinc, just put that there. We have water. We have our mass, the specific heat capacity, initial temperature, the heat, and then final temperature. So, what was the mass of a zinc? It says here 2.50 grams. So let's write that down, 2.50 grams. And for the water, 65.0 grams, 65.0 grams. And the water started off with 20 degrees Celsius. Notice how it said started off? That means it's the initial temperature. So initial temperature is 20.00 degrees Celsius. And it says later on, it rose to 22.50 degrees Celsius. So because it says later on, that's going to be your final temperature. So that's going to be 22.50 degrees Celsius. Another thing to note is that final temperature is going to be the same for both of these guys. So the final temperature for water is also going to be the final temperature for zinc, because they're all in one solution, or they just mixed together, so that's why they have the final temperature later on. So it also says that the specific heat capacity of our zinc is 0.390 joules per gram degrees Celsius. And of course for water, let's just pull out our specific heat capacity table real quick. Sorry, let me just get rid of that. Water is right over here. So 4.184 joules per gram Celsius. Let's write that down. So 4.184 joules per gram degrees Celsius. So it wants us to find the initial temperature of zinc. Now how do we do that? Normally, we'd have to find the whole equation of like zinc, right? Because the only way we can find initial temperature is if we have the equation for the heat of zinc, which is, mass multiplied by heat capacity multiplied by change in temperature. It's only if we have this equation, and then we start to transpose it and isolate the specific heat capacity. But we can't do that because we're missing quite a lot of variables. Specifically, we're missing initial temperature and heat. Thankfully for us though, we can actually find the heat of zinc because we can find the heat of water. Now how do we do that? So the heat of water, H2O, is really just the mass of water multiplied by its specific heat capacity multiplied by its change of temperature. So when you write that down, that's going to be 65.0 grams multiplied by 4.184 joules per gram degrees Celsius multiplied by change of temperature, or the final temperature, 22.50 degrees Celsius, minus the initial temperature, which is 20.00 degrees Celsius. If you put that in your calculator, the thing you should end up with is, should be approximately 680 joules. So let me just write an approximate symbol there. You might be wondering, why approximately 680 joules? Well, it's approximately because we have to follow significant figures, right? So if you don't remember, significant figures are basically just the important numbers that are being placed on the number that actually matter. So here, for this mass, we have 3 significant figures, the 6, 5, and the 0. For the specific heat capacity, we have 4. For the temperatures, we have 4 and 4. And the amount of significant figures that your answer should have should be equal to the amount of significant figures of the number here which has the least amount of significant figures. So what do I mean by that? Of all these numbers, which one has the least amount of significant figures? So this one has 3, this one has 4, these two have 4. So the smallest one is 3, right? So if the smallest one is 3, that means our answer should also have 3 significant figures. And guess what? It does have 3 significant figures. So our answer is going to be approximately something like that. So let's try to erase all this. And now that we have the heat of water, we can now find out the heat of zinc. Why? That's because the heat of zinc and water is really just inverse to each other, or at least inverse to each other in terms of their sign. What I mean by that is, the heat of water. The heat of zinc is just equivalent to negative of the heat of water. Vice versa also applies, by the way. The heat of zinc is also just negative the heat of water. So, since we know that the heat of water is 680 joules, all we have to do is put a negative, and we basically have the heat now for our zinc. So now that we have the heat for our zinc, we can now solve for initial temperature of zinc. So let's put the whole equation down. The heat of zinc is equivalent to the mass of zinc multiplied by its heat capacity multiplied by the final temperature decreased by the initial temperature of zinc. If you substitute that, what you're going to end up with is 2.50 grams multiplied by 0.390 joules per gram degree Celsius multiplied by the final temperature. Final temperature is already given. 22.50 degrees Celsius decreased by the initial temperature of zinc. So zinc is the one here that's missing. Initial temperature is the one here that's missing, right? So we have to change this entire equation such that this temperature here is going to be alone or isolated. So how do we isolate this? We can isolate this by using transposition, or basically when we just like put left side of the equation to the right and vice versa, blah blah blah. So which one can we get rid of first? Well, we can get rid of these two first because they're just multiplication, right? I mean, the temperatures here, they're covered by a bracket, so we don't really have to do anything with them first. So we can get rid of these guys. So what do? We divide both sides by 2.50 grams multiplied by the specific heat capacity, joules per gram degree Celsius. And what we're going to end up with is, we're going to end up with negative 680 joules, because remember, that's the heat of our zinc, right? Divided by 2.50 grams multiplied by 0.390 joules per gram degree Celsius is equivalent to our temperatures, 2.50 degrees Celsius minus the initial temperature. Now, why did these guys on the left disappear? That's because these guys cancel because we're dividing it, right? But since we divide also the right side, we also have to do the same thing with the left, which is why they're also here at the bottom now. The thing that's left now here is we have to isolate initial temperature, right? But this guy is still blocking the way, so we have to get rid of that. So how do we get rid of this temperature? Well, we can minus both sides of the equation by this temperature. So we're gonna have negative 680 joules all over 2.50 grams multiplied by 0.390 joules per gram degree Celsius. And all of this is going to be decreased by the 22.50 degrees Celsius. And we're going to end up with negative initial temperature. But this isn't complete yet because there's still a negative symbol, and we have to get rid of that. So how do we get rid of that? Well, we multiply both sides by negative 1. So if we multiply the negative initial temperature by negative 1, the negative symbol is going to disappear. But for the left side, the whole thing is going to be multiplied by a negative 1. And now we have the equation for initial temperature. So let's see how that's going to look like. If you put that in your calculator, you should end up with a value that's approximately 720 degrees Celsius. Again, why 720 degrees Celsius? When you put it in your calculator, you're probably going to get a really long number. But we have to pay attention to significant figures. So how many significant figures does this guy have? 3, 3, 4, 4. The smallest one here is 3. So this one also has to have 3 significant figures. So we have 1, 2, 3. So that's why we have approximately 720 degrees Celsius. And that should be your answer for this question. So for the next problem, we have a piece of gold weighing 13.5 grams was dropped into 60 grams of water. The water started at 19 degrees Celsius. Shortly after, the temperature rose by 1 degree Celsius. Your guide states that this piece of gold has a specific heat capacity of 0.130 joules per gram Celsius. What is the initial temperature of the piece of gold? Let's write down our given. So first we have gold, and then we have water. What's the mass of our gold? 13.5 grams. How about our water? 60.0 grams. And what is the specific heat capacity of these guys? So it mentions here that our gold is this, like it's already giving us the specific heat capacity. So we have to follow that. So the specific heat capacity of gold is 0.130 joules per gram Celsius. And then for water, everybody knows that's just 4.184 joules per gram degrees Celsius. Now for the initial temperatures, gold was not given, so we don't know what gold is. For water, it says that it started at 19 degrees Celsius. 19.00 degrees Celsius. Now for the heat, well, we don't know since nothing is given. But for the final temperature, it is given. So the the final temperature says that the temperature rose by 1 degree Celsius. That's not an actual answer or a value for our final temperature, but it does give us a clue. So the final temperature rose by 1 degree Celsius. So it started off as 19, right? So what's 19 plus 1? 20. And therefore, the final temperature is 20.00 degrees Celsius. Another way to think about this is that whenever we calculate stuff, notice how in the equation for heat, we have mass multiplied by heat capacity multiplied by change in temperature. Our change in temperature could also just be 1. So mc multiplied by 1. So just keep that in mind. They're both you could write the whole thing. It's really just the same thing. Anyway, let's start solving. So we want to find the initial temperature of gold, right? This is very similar to the last problem where we can't really solve for the initial temperature immediately because we're missing a bunch of variables, right? Namely initial temperature and heat. However, we can solve for heat. You know why? Because we can solve for the heat of water. We can solve for the heat of water because all of these variables are here. We have mass, specific heat capacity, and the change in temperature. And again, that's just the formula for heat. But we can sort of simplify or make the process a lot easier by just writing it all down ahead. So let's see. First, in order to find the initial temperature of gold, you want to find this variable first, right? So the heat of gold is really just the same thing as negative the heat of water. And how do we solve for the heat of water? The heat of water is the mass of water multiplied by the specific heat capacity of water multiplied by the final temperature decreased by the initial temperature of water. Sorry. Let me just there we go. Of water. But don't forget there's a negative symbol over here, so let's put a bracket over the whole thing and then a negative there. Now we can substitute our variables. So our mass 60.0 grams multiplied by 4.184 joules per gram degrees Celsius multiplied by our change in temperature, which is the 20 minus the 19, or as I just mentioned before, it's really just 1. The change in temperature is just 1. Because again, 20 minus 19, that's just 1. But for the sake of, accuracy or precision, we're just going to write the whole thing. So 20.00 degrees Celsius decreased by 19.00 degrees Celsius. Put that in your calculator and you should end up with a value that looks a lot like, hold on, it should be something like 251.04. Don't forget the negative value. But again, we have to follow significant figures. How many significant figures does mass have? 3. Specific heat capacity? 4. This guy? 4. This one? 4. The least one here is 3. Therefore, our final answer has to have a significant figures of only 3. So it should be approximately a number that only has 3 significant figures. So let's start counting from the left. So we have 2, 5, 1. 1, 2, 3. So the final number that we can only put down has to be this guy, or 1. So let's round up 1. Can we still round up 1? Let's look at the number on the right. So 0. So because it's just a 1 and a 0.0, we can't really change anything about 1 since it just stays the same, right? So our answer is going to be approximately negative 251 joules. Oh, don't forget the unit. So now we have the joules, or the heat, for our gold. Notice how this actually got a lot faster than like manually writing everything down. I mean, last time we had to solve for the heat of water, so we put a negative, and then we write it down in the heat of gold. This time, if you just write everything down ahead of time, like here, you can save a lot of time that way. Next, we have to solve now for the initial temperature of gold. So how do we solve for that? Let's look at the equation first for the heat of gold. So the heat of gold is equivalent to the mass of gold multiplied by the specific heat capacity of gold multiplied by the final temperature decreased by the initial temperature of gold. Now we could start to substitute our values here, but again, it's a lot more convenient if we just write everything down first, right? So let's try to do the transposing ahead of time. So we want to find initial temperature, right? So we have to isolate initial temperature. Same process as last question. We got to get rid of these two first because they're just being multiplied. So we divide both sides by our mass and the specific heat capacity. And we should end up with, let me just put an arrow here. The heat of gold is equivalent to the mass of gold multiplied by the specific heat capacity is now equivalent to our final temperature decreased by our initial temperature of gold. But initial temperature isn't isolated yet. We have to get rid of the final temperature. How do we do that? We have to decrease both sides, or we have to minus both sides by final temperature. So it's going to turn into heat of gold all over mass of gold multiplied by specific heat capacity decreased by final temperature. It's now equivalent to our negative of the initial temperature. Now there's still a negative out because nothing changed with this sign. It has to stay the same, but we can't let it be the same because we just want to find initial temperature. We don't want to find negative initial temperature, so we have to get rid of the negative. So what we do, we multiply both sides by negative, or we can just add a negative side on the left, and it also cancels the one on the right. So now we have the full equation for finding initial temperature. Now we can substitute. So what was the heat of our gold? So it was negative 251 joules. Also, by the way, about this, when you substitute your heat of gold, it's a thing we solved for last time, right? The proper practice is to put the value that's already rounded up to the significant figures. However, sometimes in the discussion of ma'am, she doesn't bother with that and she just immediately goes with the more exact one. I'm honestly not too sure what's the right thing to do because either way is going to have some pretty different answers. So we're going to have to ask her, but for me, I just like to do the significant figures one because it's the more scientifically accurate one. So substitute our mass. So we have, what's the mass of gold? 13.5 grams. So 13.5 grams multiplied by 1.30 0.1 30 joules per gram degrees Celsius. Decreased by our final temperature, which is 20.00 degrees Celsius, and all that has a negative sign. So put that in your calculator, and the answer you should get should be something really long, like 163.019943. Pretty long, right? But again, we have to follow significant figures. So this guy has 3 significant figures, this one has 3, this one has 4, this one has 4. The least here is 3 and 3, so our final answer should also have 3 significant figures. So let's start counting from the left. So we have 1, 2, 3, the 163. So our final digit on the right is going to be this 3 over here. But can we round up 3? Well, the number on the right of 3 is 0, so we can't really round it up to anything or round it down. So our answer is going to be approximately 163, what's the unit? Degrees Celsius. And there you have it, that's the answer. So the initial temperature of our gold should be 163 degrees Celsius. Okay, next question. During an experiment, students wanted to find out the heat exchange between 28.4 grams of aluminum and 50 grams of water. The aluminum was heated up to 100 degrees Celsius, and the tub of water was maintained at 23.7 degrees Celsius. They measured the final temperature to be 27.8 degrees Celsius. However, the students dropped the specific heat capacity index card, and thus forgot the specific heat capacity of aluminum. You, the teacher, are tasked with finding out the specific heat capacity of their piece of aluminum. So let's write our given. So we've got aluminum, that's Al, and we've got water, which is H2O. So we're going to write down our mass, specific heat capacity, initial temperature, heat, and final temperature. So how much aluminum was there? Around 28.4 grams. And we've got 50.0 grams. The initial temperature of the aluminum was 100 degrees Celsius, 100.0 degrees Celsius. And for water, it was at 23.7 degrees Celsius. The final temperature was 27.8 degrees Celsius. So we gotta find out what is the specific heat capacity of aluminum. So, in this problem, this is very similar again to the ones before, and honestly for the other problems that we're gonna be seeing later on. But this time, we're just gonna be solving for specific heat capacity. Again, we could use the equation for specific heat capacity, equation for heat, and just substitute, like as I'm gonna write right now. Hold on. See, aluminum, temperature, aluminum, and after that we just transpose until we isolate specific heat capacity, right? So how does that look like? So we have heat of aluminum divided by mass of aluminum multiplied by change in temperature, or actually I'm just going to write the whole thing. Final temperature minus the initial temperature of aluminum. It should be equivalent to the specific heat capacity of aluminum. We could unfortunately we can't substitute this right now because we're missing 2 variables, and we're missing heat and we're missing the specific heat capacity of aluminum. So we gotta find that out first. And in order to find out, again, we're missing heat, so we have to find the heat of aluminum. Fortunately for us, we can find the heat of aluminum because the heat of aluminum is just negative the heat of water. And we know the formula for this, which is just 50.0 grams. Again, I put the negative sign here because we're finding the negative of the heat. So we're going to put down the solution of heat right now. So 50 grams multiplied by the specific heat capacity. Everybody knows that's just 4.184 joules per gram degrees Celsius. So 4.184 joules per gram degrees Celsius multiplied by final temperature, 27.8 degrees Celsius, decreased by 23.7 degrees Celsius. If you put that in your calculator, the number you should end up with should be 418.4. What's the unit? Joules. Joules, because this is heat. And also, if you manually cancel out, grams cancel, the temperatures cancel, and you're just left with joules. So 4.184 joules. But again, significant figures. 3 significant figures, 4, 3, 3. The least here is just 3. So our final answer has to have 3 significant figures. So it's going to be approximately, actually wait, no. We're going to start counting from the left. We're going for the 4, the 1, the 8. So our final digit should be the 8. But can we round up the 8? Let's look at the number on the right. It's a 4. It's not above 5, so we can't round it up. So it's just going to stay as approximately 418 joules. Next, now that we have the joules, we can finally substitute for this equation so we can find specific heat capacity. So, oh, don't forget, I almost forgot the negative sign. Don't forget that. So we're going to have negative 418 joules all over the mass of our aluminum, which is 28.4 grams, multiplied by the final temperature of the solution, 27.8 degrees Celsius, decreased by 100.0 degrees Celsius, because this is the initial temperature of the aluminum that the problem gave us. Put that in your calculator and you should end up with a value of, hold on, a pretty long number, which is something like 0.509756096. A pretty long number that's something like that. But we gotta follow significant figures. So, how many significant figures in joules? 3. For mass, 3. For the temperatures, this one's got 3, this one's got 4. The least one here is 3. So we're gonna start counting from this number. 5, right? So 509. So from 9, this has to be our last digit. But can we round up 9? Let's look at that number on the right. So 7 is greater than 5, so we have to round up 9 to 10. So it's going to turn into approximately 0.510. Don't forget the unit, joules per gram degrees Celsius. Joules per gram degrees Celsius. So this is the specific heat capacity of our aluminum. However, there are different ways to write this down. You know, you could write it as 510 times 10 to the power of negative 3 joules per gram degrees Celsius. Or you could write 5.10 times 10 to the power of times 10 to the power of 2 joules per gram degrees Celsius. The preference is really just up to you. Just be careful with it's not supposed to be negative 2. Just be careful with your significant figures and stuff. But either of these 3 should be correct. And that's it. That's the answer. So the specific heat capacity of our piece of aluminum in this case is gonna be 510 times 10 to the power of negative 3 joules per gram degrees Celsius. And again, on to the next problem. An unknown piece of metal weighing about 59.047 grams was heated up to 100 degrees Celsius. It was dropped into a 100 grams tub of water whose temperature was set to be 23.7 degrees Celsius. The temperature settled to be 27.8 degrees Celsius. What is the specific heat capacity of the mysterious metal? Let's write down all our given. So for the unknown piece of metal, we're just going to put M there. Actually, no. Let's make that a capital M. Capital M. And then we got our water. So mass. What's the mass of our metal? 59.047 grams. The mass of our water? 100.0 grams. Specific heat capacity, unknown for the metal, but the water, everyone knows, such as 4.184 joules per gram degrees Celsius. For the initial temperatures, the metal was heated up to 100.0 degrees Celsius. And how about the water? It was set to be around 23.7 degrees Celsius. 23.7 degrees Celsius. And for the heat, none was given, so we don't know. And now for the final temperature, it's settled to be 27.8 degrees Celsius. So, similar process to the past problem, we just gotta find the specific heat capacity of the metal. So, what's the formula for the specific heat capacity? Let's see. So, the heat of the metal is equivalent to mass of metal multiplied by the specific heat capacity of the metal multiplied by the final temperature decreased by initial temperature of the metal. If we transpose this, you'll end up with the heat divided by mass multiplied by temperatures. It's equivalent to the specific heat of the metal. We still don't have this variable here. We're missing this variable, the heat, but we can find that out because we can solve for the heat of water using these variables. So the heat of the metal is just the same as negative the heat of water. So we can write down the equation for this, which is, what's the mass of water? 100.0 grams multiplied by the specific heat capacity of water, 4.184 joules per gram degrees Celsius, multiplied by the temperature. So the final temperature of the solution was 27.8 degrees Celsius, decreased by the initial temperature of water, which is 23.7 degrees Celsius. If you put that in the calculator, your answer should be something like negative 1715.44. What's the unit? Joules, because this is heat. Again, we have to follow significant figures because that's just how science works. So the mass has 4 significant figures because the 1, 0, 0, and the 0.0. The specific heat capacity of water also has 4, but the temperatures only have 3. So our final answer has to have a significant figure. It has to have 3 significant figures. So let's start from the left. 1, then 7, and then 1. So our final digit has to be 1. But can we round up 1? Let's look at the number on the right. 5. We can round this up because 5 is greater than or equal to 5. So the 1 turns into 2. So our final answer is going to be around negative 172 times 10 to the power of 1 joules. Why times 10 to the power of 1? Because you see, if we just ended at 2 here, we'd still be missing a 0 on the right? But again, we can only have 3 significant figures. So we can only write 3 digits. But again, we're missing a 0 pa, because look, this is in the thousands. This is 1,715, not 172. So we have to multiply it by 10, or just 10 to the power of 1, same thing, in significant figures for proper scientific notation, so we can get an actual answer. So our answer is approximately 172 times 10 to the power of 1 joules. That's the heat for the mysterious metal. And now we can substitute the values in this equation. So what was the heat of the metal? Negative 172 times 10 to the power of 1 joules divided by, what's the mass? 59.047 grams multiplied by the final temperature, which is 27.8 degrees Celsius, decreased by the initial temperature of the metal, which is 100.0 degrees Celsius. Put that in your calculator, and the value you should end up with is something like 0.40345343. Pretty long, right? Also, don't forget the unit. Since this is specific heat capacity, it's going to be joules per gram degrees Celsius. Again, significant figures. This one has 3. This one's got 4, 3, 3. 3 is the least value, so our answer has to have 3 significant figures. So this is approximately 0.403 joules per gram degrees Celsius. So the specific heat capacity of a metal should be something like that. Now this problem is pretty hard because it's going to have to be using a bit of that algebraic manipulation. So we'll see that in a bit later. For some unknown reasons, 119.1 grams worth of a mysterious concentration of hydrochloric acid, HCl, is mixed into 100 grams of water. The hydrochloric acid started off with 44.6 degrees Celsius and the water 23.6 degrees Celsius. The temperature of the solution ended up as 31.3 degrees Celsius. So what is the specific heat capacity for this unknown batch of a mysterious concentration of hydrochloric acid? So let's write down our given. So for this concentration of hydrochloric acid, and we also have water. So we write down mass, specific heat capacity, initial temperature, heat, and final temperature. So what's the mass? 119.1 grams, and water 100.0 grams. What's the specific heat capacity of both? Well, for water, everybody knows that's just 4.184 joules per gram degrees Celsius. But for HCl, it's not given because it's a thing we're supposed to solve for. What's the initial temperature of these guys? The hydrochloric acid started off with 44.6 degrees Celsius, and for water, we had 23.6 degrees Celsius. For heat though, also not given, and final temperature is given. So 31.3 degrees Celsius. 31.3 degrees Celsius. So, actually I lied a while ago. This isn't the hard part yet. It's actually one of the easier problems. So, let's just solve this. So, we're solving for heat capacity of the hydrochloric acid. Again, same process as last time. I'm honestly not even gonna solve for the formula for specific heat capacity since we've already seen it like twice already. So the formula for the specific heat capacity of hydrochloric acid is the heat of the hydrochloric acid all over the mass of hydrochloric acid multiplied by final temperature decreased by the initial temperature of hydrochloric acid. Now we have to solve for the heat of hydrochloric acid. So how do we solve that? Well, we already know that the heat of hydrochloric acid is just negative the heat of water. And we can solve for that. So negative the formula for the heat of water. What's the mass of water? 100.0 grams multiplied by 4.184 joules per gram degrees Celsius multiplied by final temperature. Final temperature is 31.3 degrees Celsius decreased by the initial temperature of water, which is 23.6 degrees Celsius. Put that in your calculator and you should end up with something that's like negative 2803.28. What's the unit? Joules, because this is heat. But again, significant figures. 3, 3, 4, 4. Least is 3, therefore significant figure should only be up to 3. Start from the left, 280. Can we round up 0? 3 is not greater than 5 or equal to 5, so we can't round that up. So it's just going to say as negative 280 times 10 to the power of 1 joules. Now that we have joules now that we have the heat for hydrochloric acid, we can now substitute it to find the specific heat capacity of hydrochloric acid. So let's put that in our calculator. So negative 280 times 10 to the power of 1 joules all over what's the mass? The mass of hydrochloric acid is 119.1 grams multiplied by final temperature 31.3 degrees Celsius decreased by the initial temperature of hydrochloric acid, which is 44.6 degrees Celsius. So if you put that in your calculator, the answer you should end up with should be equal to, if you put that in your calculator, the answer you should get should be a pretty long number. That's something like 1.76764329. What's the unit? This is specific heat capacity. So it should be joules per gram degrees Celsius. But again, significant figures. This one has 3, 4, 3, 3. Therefore, our final answer has to have a significant figure amount of 3. So it should be approximately, start from the left, 1, 2, 3, 176. Can we round up to 6? Let's look at the number on the right. 7 is greater than or equal to 5, therefore we should move 6 up by 1. So it's going to be 177, or 1.77 joules per gram degrees Celsius. And that should be the answer for that. The specific heat capacity for this mix of hydrochloric acid is 1.77 joules per gram degrees Celsius. Alright, now this problem is the one that's actually going to be pretty hard because it's going to have to deal with algebraic manipulation and stuff. So let's read it. A water bath is set with 20 degrees Celsius water weighing at about 50 grams. A piece of 40 grams of aluminum is dropped into the bath. The aluminum started off with a scorching 170 degrees Celsius. What is the equilibrium temperature? So let's write that down. So we have aluminum, right? Aluminum, Al, and we have standard water. So we have mass, specific heat capacity, initial temperature, heat, and final temperature. Now the first thing you might notice about this problem is that it really doesn't give you a lot of givens. It only gives you like 1, 2, 3, 4, like only 4 givens. That's really not a lot. But this is the fun part because if you notice, aluminum wasn't given a specific heat capacity. So in problems where the specific heat capacity isn't given, this is the time when you should pull out your specific heat capacity index card. So better make sure you have that ready. So aluminum, right? What's the specific heat capacity of aluminum? 0.904. So let's write that down. The specific heat capacity of aluminum is 0.904. What's the unit? Joules per gram degrees Celsius. What's the mass of our aluminum? 40 grams. How much water was there? There was like 50 grams of water. 50 grams of water. And what is specific heat capacity of water? Everybody knows that's just 4.184 joules per gram degrees Celsius. Now what is the initial temperature of these guys? So the water was set to 20 degrees Celsius. 20 degrees Celsius. And the temperature for the aluminum was set to a boiling or a scorching 170 degrees Celsius. That's pretty hot, by the way. Anyway, the heat, not given either, but we're supposed to find equilibrium temperature. Now, if you remember from the terminology that ma'am gave us, equilibrium temperature is, when all the temperatures just balance out, which also means that that's just final temperature. So it's telling us to solve for final temperature. Now, here's the problem. We're missing 3 variables here, So we're missing heat of aluminum and the heat of water. So how are we supposed to find any one of these if more than 2 are missing at once? So here's the thing. We have to use some algebraic manipulation and also the fact that the heat of these systems, so the heat of aluminum, is just the same as the heat of water. But of course, with a negative. So let's write down the whole formula for these guys. So what's the formula for the heat of aluminum? We have first 40 grams multiplied by 0.904 joules per gram degrees Celsius multiplied by the final temperature, which is unknown, decreased by 170 degrees Celsius. And this should be equivalent to negative the formula of the heat of water. So the mass of water is 50 grams multiplied by 4.184 joules per gram degrees Celsius multiplied by final temperature, again unknown, minus the initial temperature of water, which is 20 degrees Celsius. So if you notice, this actually looks pretty similar to some stuff we had before in like junior high or maybe even senior high, right? Where we had like a bunch of equations, right? Let's do like 7x plus 180 is equivalent to 270 minus 6x. And what they wanted you to do was just solve for the value of x. So how do we do that? We're gonna have to abuse the hell out of transposition, but this time even more of that. So how do we do that? How do we do that for this equation? So again, we're just transposing, right? Or basically, we want to make sure we can isolate the final temperatures. In order to make that simpler, wouldn't it be a lot easier to manage or deal with if we could just simplify these guys first? I mean, look, it's just grams multiplied by the specific heat capacity, and also on the right side, we have grams multiplied by specific heat capacity. So let's try to multiply those guys out first because it just makes everything a lot easier. So when we multiply these, what ends up happening is we have 36.16 joules per degree Celsius. What happened to the grams? They cancelled, man, because grams multiplied by joules per gram degree Celsius, the grams will cancel. So there's no more grams here. So we have this, right? And then we multiply it with the final temperature minus 170 degrees Celsius. Because remember, all we did was just simplify this or multiply it with each other so that it looks a lot easier to work with. And then we can do the same thing on the left. So what's 50 grams multiplied by the specific heat capacity of water? It should be somewhere like, it should be 209.2 joules per gram degrees Celsius. Again, still multiplied by our final temperature minus 20 degrees Celsius. But as you can see, this isn't isolated enough. These guys still aren't alone. So what we can do is simplify this thing even more. So we're gonna multiply our joules per degree Celsius to both of these guys, using FOIL or like just multiplying variables inside other variables. So 56.16 multiplied by final temperature, we have literally just final temperature multiplied by 36.16 joules divided by degrees Celsius. And we also have to multiply this guy to the 170 degrees. So 36.16 multiplied by negative 170 is negative 6,147.2. What's the unit? This is joules over Celsius, and we have Celsius. So the Celsius cancels out with the other Celsius. So now we're just left with joules. We do the same thing on the right side. So we have the final temperature multiplied by 209.2 joules per gram degrees Celsius, decreased by 209.2 joules per degree Celsius. Sorry, wait, I forgot to cancel the grams. There you go. Multiply this by negative 20 degrees Celsius, and you should end up with minus 4,184 joules. Now we're gonna simplify the right side of the equation because there's still a negative sign, right? So how's that gonna look like? So negative is outside the parentheses, so it should affect two of these guys. So we're gonna have negative final temperature multiplied by 209.2 joules per Celsius, and minus, actually wait, negative changing this negative, right? So negative on negative is positive, so it's gonna turn it into positive. So it's gonna be plus 4,184 joules. Let's just write down the same thing on the left side. 6.16 joules per degree Celsius minus 6,147.2 joules. Oh, 47.2 joules. Okay. Now this is a lot easier to like actually isolate. So first, let's try to get rid of this joules, right? So how do we get rid of this 6k joules? Well, we add both sides by 6,147. So add both sides by 6,147.2 joules. So these guys are going to cancel, but this is going to add up with this guy. So what's going to end up happening is that's going to look like our final temperature multiplied by 36.16 joules per degree Celsius is equivalent to negative final temperature multiplied by 209.2 joules per degree Celsius. And what's 4,184 plus 6,147? That's going to be 10,331 point, sorry, hold on, give me a minute. 10,351.2 joules. And now we can get rid, or we can combine both of these final temperatures. How to do that? Well, we add both sides by final temperature of 209.2 joules per degree Celsius. So these guys are going to cancel, but it's going to add up with the final temperature on the left. So 36.16 plus 209.2 joules per degree Celsius is final temperature multiplied by 245.36 joules per degree Celsius is equivalent to, remember, this thing is cancelled naman, 10,331.2 joules. But again, we want to isolate our final temperature. So how do we do that? Final temperature is multiplied by 245, but we have to get rid of that 245, so we divide both sides by 245.36 joules per degree Celsius. So these guys cancel, and these two will divide. So our final temperature is equivalent to 10,331.2 divided by 245 is 42.106292979. What's the unit? Degrees Celsius. Why is it degrees Celsius? Because it's temperature. And also because joules will cancel out with joules. Because this one is on top, this one is below. So our final temperature is 42.106292979 degrees Celsius. But again, significant figures. So how many significant figures do we have? This one has 2, this one has 3, this one has 3, this one has 2, 4, and 2. The least one here is 2, and therefore our final answer should also have only 2 significant figures. So let's round it up to 2 digits, starting from the left. 4 and then 2. Can we round up 2? Let's look at the number on the right. 1 is not greater than or equal to 5, so we can't round it up, and therefore our final answer is going to be approximately 42 degrees Celsius. So our final temperature for this solution is 42.42 degrees Celsius. Alright, so for this problem, same thing as last time, we're going to have to use algebraic manipulation. So let's start reading. Christian and Augustus, after watching a video online about hot balls of iron, decided to conduct an experiment of their own. They decided to heat up a ball of iron weighing 100 grams to 500 degrees Celsius. Their tub of water started off with 12 degrees Celsius. What is the expected equilibrium temperature? Also, by the way, I forgot to write it down, but the tub of water is 200 grams. So we have 200 grams of water. So let's start writing down the given. So our iron, 100 grams. Water, 200 grams. For iron, the heat capacity is 0.449. For water, everyone knows it's just 4.184. The initial temperature of iron was heated to 500 degrees Celsius. So we have 500 here. And for water, it was set to 12 degrees Celsius. So we have 12 here. Again, we're not given heat, but we're expected to find final temperature. So we have no choice but to resort to algebraic manipulation. So let's write that down. We know that the heat of iron is just the same as negative the heat of water. So we can write down now the full equation of these. So 100 grams multiplied by 0.449 joules per gram degree Celsius multiplied by the final temperature minus the initial temperature of iron is also equivalent to negative the equation for the heat of water, which is 200 grams of water multiplied by the specific heat of water multiplied by the final temperature decreased by 12 degrees Celsius, which is the initial temperature of our water. Again, we want to simplify these so that it looks a lot easier. So 100 grams multiplied by 0.449 joules per gram degree Celsius, that's going to turn into 449 joules per degree Celsius. Why is the grams gone? Because grams will cancel with the grams here. So now that we have 449, we should multiply it to our final temperature and the negative 500 degrees Celsius. So 449 multiplied by final temperature is just final temperature multiplied by 449 joules per degree Celsius. But we also have to multiply it one side to the right, to the temperature or the negative 500 degrees Celsius. So 449 multiplied by negative 500 degrees Celsius is 22,450 joules. Why did the unit change? Because joules per degree Celsius multiplied by just degrees Celsius, well, the Celsius will cancel out, so we only have joules left. Now we do the same thing on the right. 200 multiplied by 4.184 is 836.8 joules per degree Celsius. Again, grams will cancel. But we have to multiply this number with our final temperature and the temperature of water. So final temperature multiplied by this number is just, again, final temperature multiplied by 836.8 joules per degree Celsius. And then the 836 multiplied by the negative 12 should end us up with 10,000 negative 10,000 41.6 joules. Now it's time to simplify. Let's destroy, or let's break down this parentheses, and it's gonna end up looking like, so you write everything, final temperature multiplied by heat capacity decreased by the joules, which is 40 joules. Again, breaking down the parentheses. So the negative here is gonna start affecting both of these guys. So negative, it's gonna be negative final temperature multiplied by 836.8 joules per degree Celsius. And again, negative affecting another negative, that just turns into positive. So it's gonna be, plus 10,041.6 joules. Now this is so much easier to isolate. So we want to try and get rid of the joules, and we want to try isolating the final temperature. So we're going to add both sides with 22,450 joules. That's going to end up with, on the right side, it's going to be 33,000. Wait, sorry, is that right? Yeah, 32,000. It's going to be 32,491.6 joules. But we still want to isolate paman, or we still want to combine the final temperatures. So what we're going to do is we're going to add both sides with final temperature multiplied by 836.8 joules per degree Celsius. These guys are going to cancel, but it's also going to add with the 449 on the left. So we're going to be ending up with, on the left side of the equation, we have final temperature multiplied by 881. 881 point, sorry, 881.7 joules per degree Celsius. So now this is looking pretty easy, right? It's looking pretty easy to isolate. So we have to isolate final temperature. So we have to get rid of 881 here. How do we do that? We divide both sides. By 881.7 joules per degree Celsius. So our final temperature, again, these guys are going to cancel, is going to be equivalent to, what's 32,491 divided by our 881.7? That's going to be 36. It's going to be a pretty long number. 36.85108313. What's the unit? It's going to be degrees Celsius, because again, this is temperature, and also because joules divided by joules per degree Celsius is just the same thing as joules over 1 multiplied by the reciprocal of this, which is degrees Celsius divided by joules. So these guys cancel, and we're just left with degrees Celsius, which is why we have degrees Celsius for our answer. But again, significant figures. This one has 3, this is 3, this is 3, 4, 4, but 2. The smallest one here is 2. So our final answer has to have only 2 significant figures. So this is approximately 2 significant figures, right? So start from the left, 3 and then the 6. Can we round up the 6? Let's look at the number on the right. 8 is indeed greater than 5, so we have to round up 6 by 1. So 36 turns into 37. So it's approximately 37 degrees Celsius. So the final temperature of the whole system is approximately 37 degrees Celsius. Alright, now for our 8th problem. So, Janico was tasked to conduct a similar experiment to Christians and Augustus. This time, he heated a 150.0 gram piece of gold to 300 degrees Celsius. There was supposed to be 300 degrees Celsius here, but I forgot to write it down, so let's just place it down ahead. He then dropped the gold into a coffee cup calorimeter filled with 50.0 grams of water. The water was originally set to 25 degrees Celsius. Later on, the temperature of the mixture settled to 45 degrees Celsius. What is the specific heat capacity for the gold? So let's write down our given. The gold is 150 grams, 150.0 grams. The water is 50.0 grams. The specific heat of the gold, not given, because we're supposed to solve it. And the specific heat of water, everybody knows, it's just 4.184. The initial temperature of gold, again, is just 300 degrees Celsius. I just forgot to write it in the problem. The initial temperature of the water though was 25.0 degrees Celsius because it was originally set to 25 degrees Celsius. Next, what is the heat? The heat here is not given at all, so it's just an empty slate. But we do know the final temperature of the mixture, which is 45.0 degrees Celsius. 45.0 degrees Celsius. Again, they want us to find the specific heat capacity of gold. Now we already know the formula of this. We've seen it a lot of times before in the past problems, and it's just the heat of gold divided by the mass of gold multiplied by final temperature decreased by the initial temperature of gold. But the thing is, we're missing the heat of gold. Thankfully for us, we can solve the heat of gold because we know what the heat of because we can solve for the heat of water because we have all the variables in check. So we know that the heat of gold is equivalent to negative the heat of water, and we can solve for this. So the formula for water, or the heat of water, is the mass of water, 50 grams, multiplied by the specific heat of the water, which is 184 joules per gram degrees Celsius, multiplied by our final temperature, 45.0 degrees Celsius, decreased by 25.0 degrees Celsius. So put that in your calculator and you should end up with a value that's approximately, let me change that sign to approximately negative 418 times 10 to the power of 1 joules. You could also just write this as 4.18 kilojoules. It's really just up to your preference, as long as the significant values are just the same or they're correct, and you have their actual accurate numbers. So now that we have the value for the heat of gold, we can now plug it in this formula. So we have negative 418 times 10 to the power of 1 joules all over the mass of gold, which is 150.0 grams, multiplied by the final temperature, 45.0 degrees Celsius, decreased by 300.0 degrees Celsius. So put that in your calculator and you should end up with a value that's pretty long. It should be 0.109281048. What's the unit here? This is specific heat capacity, so joules per gram degrees Celsius. Again, we gotta follow significant figures. So this one has 3, this one has 4, this one has 3, this one has 4. The least here is 3, and therefore our final answer has to have a significant figures of 3. So it's gonna be starting from 1, 1, 2, 3. Our final value, or final digit, has to be 9. Can we round up the 9? Then let's look at the number on the right. 2 is not greater than or equal to 5, so we can't round it up. So it's just gonna stay the same. So our answer is approximately 0.109 joules per gram degrees Celsius. So that's the specific heat capacity of our gold. Another way to write this is also 1.09 times 10 to the power of negative 1 joules per gram degrees Celsius. Now, for our second to the last problem, let's read. An unknown amount of PT, also known as platinum, was dropped into 0.125 kilograms of water. The piece of platinum started off at 20 degrees Celsius. Meanwhile, the water was at a boiling 100 degrees Celsius. In the end, the temperature balanced out to 35.0 degrees Celsius. What amount of platinum was dropped into the water? So, let's write down our given. We have platinum and we have water. So we have mass, specific heat capacity, we have initial temperature, and then we have heat, and finally, final temperature. So, what was the mass of the platinum? We don't know, because again, it's asking for what amount of PT, and also it's not given, so we're going to have to leave that blank. But what is the mass of the water? It's 0.125 kilograms, 0.125 kilograms. But during our calculations, we want to use grams, so we have to convert this. So multiply this by, for every 1,000 grams, there is 1 kilogram. And these guys cancel. Therefore, we have 125 grams. Next, what is the specific heat capacity of platinum? Again, it's not given here, so we're going to have to look at our index card. So let's find platinum. Platinum is over here. So we got 0.133. So we got to write that the specific heat capacity of platinum is 0.133. 0.133 joules per gram Celsius. Now for water, everyone knows it's just 4.184 joules per gram degrees Celsius. Now what is the initial temperature of platinum? It says that it started off at 20 degrees Celsius. So 20 degrees Celsius. And the water was at a boiling 100 degrees Celsius. 100 degrees Celsius. The heat, not given for both of them. But what is given is the temperature balanced out to 35 degrees Celsius. So our final temperature is 35.0 degrees Celsius. So, what are we tasked to find? What is the mass of the platinum? For the mass of the platinum can be calculated using the formula for the heat of platinum. So let's look at the formula for the heat of platinum first. So heat of platinum is equivalent to mass of platinum multiplied by the specific heat capacity of platinum multiplied by final temperature decreased by the initial temperature of platinum. So we want to find mass. So in order to isolate mass, we have to get rid of specific heat capacity and the temperatures. So we have to divide both sides by specific heat capacity and the temperatures, or the change in temperature. So if you manage to do that, these guys are going to cancel, and what you're going to end up with is the mass of our platinum is equivalent to the heat of platinum divided by the specific heat of platinum and the final temperature decreased by the initial temperature of platinum. So now that we have the equation for the mass of platinum, can we substitute our values in? We can't, because we're still missing the heat of platinum. This is still empty. So we have to solve for that. How do we solve for that? Well, we can solve for it by finding the heat of water. And thankfully we can, because all the variables are just here for us. So we know that the heat of platinum is just equivalent to negative the heat of water. And we can write down the equation for this as 125 grams multiplied by 4.184 joules per gram degrees Celsius multiplied by 35.0 degrees Celsius minus 100 degrees Celsius. Put that in your calculator and you should end up with a value that is something like negative 15.168. Oh, sorry, no, that's the wrong that's the wrong one. It should be close to 33,995 joules. But again, significant figures. 3, 3, 3, 4. The least amount is 3, therefore our final answer has to have 3 significant figures. So start from the left. 1, 2, 3, 9. Can we round up 9? Let's look at the number on the right. Yes, we can. So 9 turns into 0 and the 3 turns into 4. So our final answer is going to be approximately 340 times 10 to the power of 2 joules. Or you could write this as 34.0 times 34.0 kilojoules. The preference is really just up to you. Whatever floats your boat. So now that we have the heat of platinum, we can substitute these values into the formula that we made here. So let's write that down. 340 times 10 to the power of 2 joules divided by the specific heat capacity of platinum, which is this 0.133 joules per gram degrees Celsius multiplied by 35.0 degrees Celsius decreased by 20 degrees Celsius. Put that into your calculator, and you should end up with a value that looks a lot like this. 0.1092810. Oh, sorry, wait. That's the wrong one again. My bad. Should be equivalent to a pretty big number, which is 17,042.60652 was the unit grams because this is mass. But again, significant figures. 3, 3, 3, 2. So our final answer has to have a significant figures of only 2. So let's start rounding up, or let's start changing it. So from the left, we have 1 and 7. Can we round up 7? The number on the right is 0, so we can't round it up. So we're going to end up with approximately 17 times 10 to the power of 3 grams. Or, better yet, 17 kilograms. So the amount of platinum that was dropped into this boiling pit of water was 17 kilograms. There was 17 kilograms of platinum. So, now we have our final problem. Let's read. Sean is tasked with cooling off a 40 degrees Celsius 100.0 gram piece of silver. At his disposal is a faucet that releases water constantly cooled to 10 degrees Celsius. He is supposed to cool down the solution of golden water to 12.6 degrees Celsius. How much water should he use to cool off the piece of silver? This problem is very similar to last time, except this time we're solving for the mass of water, because it's asking how much water should he use. So, let's start solving. Let's write down our given first. So for silver, we have 100.0 grams. For water, not given, because we're supposed to solve how much water. What is the specific heat of silver? Let's look at our index card. So our index card says that silver has a specific heat index of 0.235. So let's write that down. 0.235 joules, 0.235 joules per gram degrees Celsius. And what is the heat capacity of water? Again, same as always, the 4.184. What is the initial temperature of our silver? It says that it was at 40 degrees Celsius. So we write 40 degrees Celsius. And for water, 10 degrees Celsius. And the final temperature should be 12.6 degrees Celsius. So it asks us, how much mass of water, how much water should we use so that we can reach this final temperature? So let's find what the equation of mass of the water is. Again, this is just the same thing as last problem, except for this time we're solving for water. So the formula for this is the heat of water divided by the specific heat capacity of water multiplied by the final temperature, 12.6 degrees, the final temperature, TF, decreased by the initial temperature of water. We can't use this equation yet because we don't have the heat of water, but we can solve for it because we can solve for the heat of silver. And we know that the heat of water is just the same as the heat of silver, but with a negative. So let's solve for that. So the mass of silver multiplied by the specific heat capacity of silver, which is 0.235 joules per gram degrees Celsius, multiplied by our final temperature, which is 12.6 degrees Celsius, minus our initial temperature for silver, which is 40.0 degrees Celsius. Put that in your calculator and you should end up with a value that is around 643.9 joules. These signs just cancel, so that's positive, but we gotta round this up to the significant figures. So this one has 4, this one has 3, this one has 3, and this one has 3. So our final answer should have 3 significant figures. Let's start from the left. 1, 2, 3. Can we round up 3? Yes, we can. So it turns into 644 joules. Remember, it's a positive because these two negatives cancel out. So now that we have the heat for our water, we can plug it in this equation. So 644 joules divided by the heat capacity of water, which is 4.184 joules per gram degrees Celsius multiplied by the final temperature, which is 12.6 degrees Celsius, decreased by 10 degrees Celsius. Now, put that in your calculator and you should end up with a pretty big number or long number of 59.199888234 grams, because this is mass. Again, we gotta round this up to the right amount of significant figures. So we've got 3, we've got 4, we've got 3 on this one, we've got only 2 on this one. So our final answer has to have 2 significant figures. So from the left, 5, 9. Can we round up to 9? No, we cannot. So it's just gonna be equivalent to 59 grams. So Sean would have needed 59 grams of water to cool off this piece of silver. And that's your final answer. Thanks for watching, and just keep practicing. And also make sure that when you practice, try to make sure that you can learn how to convert units, because I'm very sure that ma'am is gonna start putting those into the question, so it's gonna be even more difficult. All these stuff, there wasn't really that much conversion, but you should prepare for that regardless. So thanks for watching, bye bye, and good luck with prelims.